Okay. Hello, everyone. I think that it's time to start the next session. The next session will be about smart embedded systems. I'm Cristian Pilato from Politecnico di Milano. I'll be chairing this session. The first paper is about thermal-aware lifetime reliability optimization for automotive distributed computing applications. And if you have any questions, write them in the chat. And then I think there will be one of the authors to answer to them.
Hello everyone, I am Ajinkya Bankar from Florida International University. I am going to present my research topic, Thermal Aware Lifetime Reliability Optimization for Automotive Distributed Applications. My collaborators are Dr. Shisha from the Vikes University, Dr. Vivek Chaturvedi from IIT Palakkad, and Dr. Gangkwan from Florida International University. Temperature is a critical factor for automotive system reliability because if we see automotive electronics failure, 20% is caused by vibration and shock, then contaminants and dust cause 6%, humidity moisture 19%, and temperature cause 55%. So there are two aspects. The first is when maximum temperature threshold is reached by the processor or ECU, it is automatically shut down. Suppose if we consider a brake-by-wire system where if you press the brake pedal and if that ECU is already shut down, you will not be able to apply the brakes and you will face a major consequence. Second issue, if the high temperature is there, it will accelerate the wear out mechanism and it will reduce the lifetime of the device. So in this research we consider different problems like how to guarantee peak temperature, how to optimize latency, temperature and system level reliability. We have contributed with mathematical model for thermal behavior. We have considered genetic method for peak temperature bounding and efficient system level MTDF calculations. Our system models, we model vehicle application with the task graph where each node represents a task and each edge represents worst case communication cost between two tasks. For each task node, we have different worst case execution time on different ECUs. We want to map this task graph on the heterogeneous ECU architecture. We consider total power as a combination of dynamic power and leakage power. We have considered conventional RC thermal model. We model lifetime reliability as a mean time to failure for the electromigration. We consider this problem statement to guarantee peak temperature below threshold, to minimize the latency, to minimize peak temperature, and to maximize the MTTF. So this is our first contribution. Here we have presented a mathematical program for simple thermal behavior where we consider a constant stable state temperature for each task and then we find the temperature bound. Later on we found that it's a very pessimistic approach when execution time of the task are shorter as compared to the period. Also it takes a lot of computational time and it's really difficult to incorporate system level reliability in the model due to non-linear nature. To overcome these problems, we decided to go with the genetic programming method. There we consider two problems like how to bound the peak temperature and how to calculate system level MTDF more efficiently. The peak temperature bounding simple thermal approach that we have considered before, it's very pessimistic. There is one more in the literature, step up schedule, but it fails sometimes. Let's see with the help of example. This is a two task step up schedule for two periods. From the experimental setup, we get a peak temperature at this point. Now the idea is, if execution time of task 1 is nearby 0 in the second period, we get a schedule like this, and we get a peak temperature of 94.02 degrees Celsius, which is higher than the peak temperature bound given by step up schedule. So it's a failure of step up schedule. To overcome this problem, we have presented this algorithm. Let's understand with the help of example. Suppose we have a periodic schedule of 4 tasks. As per the first step, let's calculate stable state temperature Tm. Second step, calculate individual task stable state temperatures. And now for each task, let's say task V1 comes. Now compare its temperature with the Tm. Suppose it is below, so we skip this task, we go to the task number V2. Again compare the temperature, suppose it is above the Tm. So as per this step, we execute and update the value of Tm. Then comes task number 3. Its temperature is below Tm, this updated Tm. So we don't consider this task, and then we go for task number 4. Suppose its temperature is greater than the updated Tm. So we execute this task, update the value of Tm, and then we go for the next step. This gives the temperature bound because the V4 is our last task. We have proved this theorem. It guarantees that the peak temperature bound given by this algorithm is high enough to bound variable execution time scenarios. Efficient system-wide reliability calculations. This is the existing model. It runs from 0 to infinity, and therefore it consumes a lot of computational time, and it limits the design space exploration. To overcome this problem, we have proposed this new model. It's a very efficient model in terms of time. It's a closed form, and the error between this model and the existing one is just below 0.1%. Our experimental setup, we have considered 3 ECUs with different ambient temperatures. We have generated task graphs randomly for 10, 15, 20 and 25 tasks. Our power consumption is in this range. Our testing approaches, we have considered mathematical program for temperature oblivious, where no thermal behavior is considered. Simple thermal approach, where we have proposed earlier. Then we have genetic algorithm for peak temperature bounding proposed, as well as fast MTDF calculations that we have proposed. And the last is again genetic algorithm with the peak temperature bounding that we have proposed along with the existing MTDF calculations. We call it traditional MTDF calculations. So these are our experiment results. Let's see the peak temperature of simple thermal approach, orange color. If you see with these proposed temperature bounding mechanisms, this simple thermal approach is having very high peak temperature in all the test cases. So it's really pessimistic. In terms of MTDF, the method that we have proposed for MTDF calculation and the existing method, they have almost similar MTDF values for all the task cases. For MXPAN, the method that we have proposed for MTDF calculation and the existing one, they have almost similar MXPAN. You may observe for all the cases. But there is a big significant improvement for CPU time for our proposed MTDF calculations as compared with the existing method. You can observe it for all the cases. So in summary, temperature is a critical factor for system level reliability. We have considered mapping of the vehicle application to heterogeneous ECU architecture. We have proposed mathematical program To overcome its drawback, we have proposed genetic algorithm where we bound the peak temperature very efficiently. Then we have proposed time efficient method to calculate system level reliability. From our experimental results, we find that simple thermal approach temperature bound is pessimistic as compared to what we have proposed and used in the genetic algorithm. And for the similar performances of MTTF, MaxSpan, our proposed MTTF formulation achieve a significant improvement in the CPU time. So thank you for your time. I would like to have your questions.
So, welcome back. Let me unmute if I find it. Okay, it's already muted. The author, is there any question for the author? I don't see any of them in the chat, but I may have one if I can. My question is very simple. Why did you choose to use a genetic algorithm? Is there any specific reason for using this kind of meta heuristic, or was just a way to explore the design space?
Actually, we were trying mathematical program, and to include the reliability, it's a exponential term, one of the exponential term, and we were not able to incorporate that exponential term into the mathematical model. We could have used linearization for that exponential term, but that was taking a long time. So we decided to go with the genetic algorithm so we can use all these non-linear terms into the calculations.
Now that was okay for the comparison with mathematical forms. Well, what about, for example, simulated annealing or taboo search? I mean, I expect that you use just genetic algorithm just to include those in exploration framework, but you could use any of them.
Yeah, we could have used it, but we just decided to go with genetic.
Oh, okay. Okay. So it's just an application of that. Okay.
Yeah.
Okay. Any other question? Okay. Thank you. Thank you for your presentation and for your presence here. I think that we can move to the next speaker. The next talk is about on-chip voltage temperature digital sensor for security, reliability, and portability. So let me move to the...
Hello everyone, I'm going to present our paper on chip voltage and...
One second.
Hello everyone.
So let me share screen.
I'm going to present our paper on chip voltage and temperature detail sensor for security, reliability, and portability. I'm MD Tawfiq Hassan Onik. This work is a joint effort of University of Maryland, Baltimore County, and Securicy and Telecom Paris. In real life, chips are designed to work under well-defined conditions. While designing chips, founders defined that the PVT corners as process, voltage, and temperature corner, the condition in which chips are supposed to operate nominally. But in lifetime, it can go through different kind of stress or attacks, like it can go through under or over power supply and experience very high or low temperature, which can violate the PVT corners. To keep track of anomalies, it is important to monitor the operating conditions continuously. So here we develop an integrated framework to monitor chips voltage and temperature via designing an embedded detail sensor assisted with machine learning neural network. We know that the analog sensor is different than digital sensor in different parameters like layout, portability, and calibration techniques, and so on. For time check, I'm not going to discuss it, but because of the superiority of digital sensor over analog sensor, it got a lot of attention these days. So here in this research, we use digital sensor. Here is the architecture of our targeted digital sensor, which consists of artificial critical path. It includes N0 initial buffers and N1 post buffers are connected with individual flip-flop. When the voltage or temperature changes, the delay of the critical path also changes. So the flip-flop carries different sequence of values. To catch the effect, we propose two methods. First one is the matrix-based method called AMBM, where it extracts the output of individual flip-flop or I consecutive clock cycle and generate these types of matrix for each VT pairs. Second one is the average-based method as ABM. Here it extracts the index of the first flip-flop whose phase is different from its previous flip-flops, and then it generates the average flip-flop number as AFN. Here you can see that first phase change is happening as flip-flop 31 for all clock cycle, so the AFN is 31. As in this example over here, it can also experience multiple phase changes, but we consider only the first changeover, and we found the AFN is 13. For predicting the operating condition, we use matrix and AFN values. Note that the AFN and matrix can be similar for some VT pair, as you can see from this figure. For example, these two blue points for different VT pairs have same AFN values. It shows that the relation between the matrix and the AFN for VT pairs is not 1-to-1. Therefore, we use dual sensor that operates under same temperature. However, the VDD of one has the constant shift than another one. Then based on this outcome of these two sensors, we can find the voltage and temperature accurately. This is the setup we use for our experiment, and we use simulation data for training and the neural network, and we extract the outcome of the sensor during the runtime and use it for predicting the V and T. For predicting the voltage, we have two different models. First one is the NN1, use the temperature and the matrix S, and second one is the NN2, use the temperature and the AFN. Here we change the model with 3 to 15 sensor pairs and test with all rest of the sensor pairs, and found the average voltage error goes to 0.005 volt when trained with 15 sensor pairs. It shows that the training with large number of sensor pairs decreases the error. Also, process variation effect decreases. Then we do k-fold cross validation, where we consider one of the sensor for testing and the rest of 15 sensor for training. We observe that the results are very promising as the errors goes very low. And we use NN3, which predicts the both voltage and temperature based on the matrix S. And the result shows that if we train with 15 sensors, the average voltage error goes to 0.014 volt, and average temperature error goes to 2.5 degrees Celsius. Also, the k-fold cross validation shows that the results are stable over different sensors. To summarize, as we know, anomalies can be detected via sensing circuit operating conditions. Here, the detail sensor associated with neural network can predict voltage and temperature. Result shows that the process variation does not impact the assessment, and the voltage and temperature can be predicted with good accuracy with this framework. And thanks for your patience. Please drop your questions. We will be happy to reply soon. Thank you.
Okay. Let me. Okay.
Hi everyone, today I'm going to share with you how the SNAP software works. So SNAP is a secure collaborative platform for online, mobile, and paper surveys.
Oh, wait, some problem with the YouTube. Any question for the speakers? Is there any question? Just a personal question. Can you elaborate more on the type of security threats that you can address with your sensors?
So basically, we are thinking about the security, like when the security comes over here. So what we think first? So we think that, okay, the attacker will come and change the operating condition, like it will change the voltage and the temperature. So that's what we considered over here. So we're thinking that, okay, maybe when the attack comes, your voltage or temperature will be getting shift from the nominal one. So that's what we are trying to catch from our sensor over here, and it will, like, I can say that it will efficiently catch the voltage and temperature. Based on that, we can see that, okay, if it is in a good range or not. If we see that, okay, if it is in not good range, maybe it can give you some wrong values, so which is not good for your system, right? So that's what we are trying to capture over here.
Okay. Thank you. any other question from the audience for the attendees? What do you think is your next step in this research?
Sorry, can you please repeat it again?
Yeah, what's the next step in this research?
So what we are going to do is we already tried to check it on our FPGA level. So we'll try to take it on our chip level as well. So we'll try to implement in the silicon chip, and we also try to do aging analysis on top of it. And then we'll see that, okay, even if our sensor is getting A, so how this might give you the answers, or if it is like, okay, our results is shifting, so how we can mitigate that with different kind of calibration techniques and so on. So like that's we are really hopeful, and let's see how far this goes on.
Okay. Okay, very good. Okay. Any other question from the audience? Okay, if not, thank you for your presentation and also for being here for answering the questions. So we can move to the next presentation that is about rethinking mixed criticality architecture for automotive industry. And let me play the video.
Hello everyone, welcome to this session, and I'm very glad to see you guys during this special time. My name is Zhejiang, and I'm a system design engineer in ARM. At the same time, I'm also a research associate in University of York. Today I'm going to talk about our latest paper called Rethinking Mixed Criticality Architecture for Automotive Industry. This paper is also contributed by other experts whose name can be found in this slide. In today's presentation, we will have 5 parts. We will first go through the background and the research challenges in the first 3 parts. Afterwards, we will discuss our proposed solutions. At last, we will make the conclusion. Now, let's start from the first part. Recently, the popularity of the safety-critical system is very high due to the development of CPS. The popular direction including autonomous systems, Industry 4.0, and IoT. In safety-critical system, mixed criticality systems is a very important direction. Take autonomous system as an example. Nowadays, the electronic system in a vehicle is very complicated, which can be simply classified into chassis control, body control, and driver information systems. In industry, the development of these functionalities are under different requirements, which is also called different criticality levels. Currently, these different criticality functions are implemented in separate chips. They are more like a distributed system. However, the main trend of the future is integrating all these functionalities in a single chip. This is mixed criticality system. Nowadays, the MCS is well studied in academia, but is providing difficulty to implement in industry, as the theoretical model do not always consider industry standards and practice. Now, let's see the state of the art in academia. The state of art research regarding MCS is triggered by real-time system community, in which meeting real-time requirement is the key. To meet the real-time requirement, getting an accurate WCET is the first step. WCET means the worst-case execution time. Here, we have a diagram to show the WCET of a task. As shown by this diagram, it is very unlikely to achieve the WCET of a task while the measurement. In MCS, WCET is normally predicted with different levels of confidence. It can be high confident, which is pessimistic and safe, but it's with with the system resource. It can be also no confident, which is optimistic and saves system resources, but it is risky and dangerous. Note that here we only talk about 2 criticality levels. In practice, we may have 3 or 4 criticality levels. The earliest methodology of the MCS is provided by Vista, and he is an expert from Honeywell. He adopted a very conservative system model, which lets the system always running in a high confidence mode. This means the system is safe, but the utilization of the resource is very low. Recently, the most popular MCS model brings the concept of the system mode switch. So, what is the system mode switch? The system starts at the no criticality mode, which is no confident but efficient. When something goes wrong, for example, a fault or task over-execution, the system will change to high criticality mode, and the no criticality tasks will be terminated in order to guarantee the correct execution of the high criticality tasks. In order to achieve the system mode switch, a system monitor is definitely required. It can be implemented in an operating system or independently. In academia, a lot of theoretic analysis is ongoing with this model. For example, how to make the schedulability analysis accurate, how to improve the model. However, in industry, how to build such MCS is still a problem. Now let's say these problems. These problems is mainly caused by different mismatches. The first mismatch is related to the mode switch. As we mentioned just now, mode switch is the key strategy in MCS. However, as per industry state of art, triggering a mode switch based on task criticality levels are not correct. Since the criticality level of a task is determined by multiple factors. Here, we have an example of ISO 26262, which is the safety standard for automotive industry. According to ISO, the criticality level of a task is determined by severity, exposure, and contributivity. However, here, only the severity determines the result of terminating a task. For example, it is possible to terminate a low criticality task with high severity and reserve the high criticality task with no severity. Secondly, dependency is also taken into account. If a high criticality task depends on the result from a low criticality task, during the mode switch, if we terminate the low criticality task, the high criticality task will also execute wrongly. At last, isolation must also take into consideration. As regulated by ISO, the different criticality components must be isolated, which avoids the fault propagation between different critical components. In this paper, we propose the ZMCS, which is focusing on the 3 key mismatches between the academia and the industry in MCS. To solve the mismatch 1 and 2, we provided a 2-level safety analysis, which must be executed before a mode switch. The safety analysis can make sure we terminate the correct functions and tasks during a mode switch and reserve the correct functions. Moreover, we also provided 3 potential solutions of the mixed criticality architecture, which are software virtualized system, ARM trust zone-based system, and hardware-assisted system. They are specifically introduced and compiled in our paper. Due to the time limits, we will not go through the details of these designs, but I'm very happy to talk about them offline, so feel free to ask any questions regarding the design details. To make a conclude, MCS is the key direction in safety-critical systems. It is well studied in academia, but still have gaps in industry. In this paper, we propose the runtime safety analysis and 3 system architectures to solve these gaps. The main intention of this paper is to encourage more frequent and tighter connections between the academia and the industry. Thank you for your listening, and please let me know if you have any questions, comments, or concerns. Thank you.
Thank you for the presentation. Any question from the audience? I think there is one question that is, how do you define your criticality?
Okay. Hi. Can you hear me?
Yes, sure.
Thank you for the question. So actually, the criticality, in this paper, we have 2 concepts of the criticality. The criticality of the tasks of the components has to acquired from the safety analysis, and this is usually guided by the safety standard, like the ISO 26262, and we have the assessment to get this criticality levels, and this is a concept in the industry, and in the academia, people also have another concept for the criticality of the system mode, and I think this one is more determined by the system situation. If the system is in a urgent situation, they call it is a high criticality mode, and if the system is in a stable or normal situation, and they call it no criticality mode. So they are a little bit confused for 2 concepts. Yeah, thank you.
Any other question? And there is another question from the same attendee, that is, how do you actually quantify the level of criticality?
Yes, also good question. This one is also given by the safety standard. For example, given by the ISO 26262, we have 4 levels of the criticality levels, and they have 2 factors to determine these levels. For example, in the highest level, they have 2 factors, one called the SPFM, one called the LFM. So in the highest
I'm Sang Park from
sorry?
No, go ahead.
For the highest criticality level, the safety standard regulate, we need to have the 99 coverage for the SPFM and the 90 coverage for the LFM. So this is give the quantity result of these criticality levels. It is normally get from the safety analysis, and the target is given by the safety standard. Yes, thank you.
Thank you.
Thank you for the question. Yeah.
Yeah. Any other question? Otherwise, I think that if you have any other question, I think the author will be happy to continue the discussion offline, and we can move to the last but not least paper of this session. Okay, thank you very much for your presentation and also for your answers. We can move to the, as I said, to the last but not least paper of this session, that is about design time optimization of reconfigurable PV architecture for irregular surfaces. So let me share the video.
Technical University of Berlin, and today I will present our paper, Design Time Optimization of Reconfigurable PV Architectures for Irregular Surfaces. PV arrays are broadening the reach to various applications, and PVs have been considered usually for large PV farms with uniform architecture, but they are now being integrated into buildings and also electric vehicles. They have benefits in reducing the charging burden and eliminating the conversion process and directly using solar energy in electric vehicles. There are certain characteristics in PV power generation, and therefore the PV arrays require a technique called maximum power point tracking to let them operate in the efficient region. However, there are effects such as partial shading effect, where shadows of nearby obstacles or dust on a part of a PV array limits the current of all the PV modules in a series connected string, as you can see from the bottom right corner. And in this figure, bottom left panel is covered with dust and is unable to generate electrical current. And the PV module, which is connected in series, receives enough sunlight, but still not being able to generate the electrical current. In order to avoid that, bypass diodes could provide an alternative current path, as shown in the red arrow. Reconfigurable PV architectures has been considered to tackle partial shading problems. 3 sets of switches, 2 for parallel connection between the adjacent PV modules, 1 for series connection, could be used to dynamically reconfigure the array. And a parallel connection of low irradiance cell generating little current helps in letting the PV modules to operate in the region closer to maximum power point. For example, if you look into PV group 3, it consists of 5 PV modules, where PV group 2 consists of 3 PV modules. If the sums are similar, sum of maximum power point currents of group 2 and group 3 are similar, all are able to operate near the maximum power point. In this slide, I will explain the motivation of our problem. PV arrays on irregular surfaces are also subject to a non-uniform solar irradiance, but the pattern is very different to partial shading scenarios. Uniform placement of reconfiguration switches makes sense because the probability of partial shading is often assumed to be uniform. However, probability of occurrence of non-uniform solar irradiance is not uniform on irregular surfaces, but rather dependent on the curvature of the surfaces. And also, solar irradiance values show a continuous spectrum as opposed to partial shading, where there is a few number of modules receiving distinctly different little solar irradiance from others. So it is better to place reconfiguration switches at selected locations to tackle the non-uniform irradiance due to irregular surface. This will provide a cheaper solution than using multiple microinverters, and this requires less number of switches than prior reconfiguration architectures tackling partial shading. Here I will state the problem of PV reconfiguration switch location determination. Objective is to maximize the power generation of a PV array for a given set of light source. It can be described as follows. P average is the mean of the maximum power points for n different light sources. The control knobs are the atomic unit size determination and a placement of reconfiguration switches, which will divide those atomic units. Inputs for the problem are solar irradiance angles and shape of the surface. Then there are constraints on the number of cells in series, which will help in achieving the input range constraint from the inverter side. And then there is a constraint on number of reconfiguration switches. So once the number of reconfiguration switches is given, then we determine the optimal placement of those switches. Flexibility of reconfiguration is crucial in adapting to different solar irradiance scenarios. For example, if 120 cells or modules were to be configured into 10 groups of equal size, meaning that there are 9 reconfiguration switch sets in between each group, There are 6 ways to do so. Each group will comprise 12 cells because there are 10 groups. And then this atomic unit or group can have the topology of 12 cells in series and 1 in parallel, 6 cells in series and 2 in parallel, 4 by 3, 3 by 4, and so on. And as described from the previous slide, the total number of cells or modules in series has to be met. It is 24 cells in the figure below to meet the input voltage range constraint from the inverter. Among the available ways to divide, 6 by 2 and 1 by 12 cannot meet the 24 series cell constraint, even if all units are series connected. If you look into 2 by 6 and connect all 10 groups in series, it'll still have 20 cells in series. So using 12 by 1 unit allows 2H8 number of series parallel configuration, which equals 9 series parallel configurations. Because if you look into the right-hand side figure, if you place 2 12 by 1 series groups in series, then you will have 24 cells in the series direction. And the remaining 8 could be connected, remaining 8 groups can be connected in parallel to the groups. So G1, G2, G1, G1, something like this. And then you're coming up with the sequence of 8, selecting group 1 or group 2. This becomes combination with repetition, denoted often by this notation H. If you use 6 by 2 units, then you will have 84 configurations, giving more flexibility than 12 by 1. Now I'll describe a subroutine of the dynamic reconfiguration algorithm. So given solar irradiance and location of switches, dynamic reconfiguration algorithm, similar to prior works tackling the partial shading, is performed. In step 1, we divide the parallel groups of equal size. And step 2, calculate the sum of maximum power point current for each group. And we remove one atomic unit from the group with the largest sum of maximum power point current and add it to the group in the string next to it. For example, the second group from the top has the sum, which is the largest, 9.3 amperes. And then the third group from the top has the minimum sum. So you could move one atomic unit from the second group to the third group to balance the sum of maximum power point currents. If the step 4, if the difference in the sum of maximum power point current is larger than the threshold, then you go back to step 2. Otherwise, you end the algorithm. So the final result would be that the units within a group are connected in parallel, and each group is connected in series. And then this will let each modules to operate near the maximum power point region. Making use of this subroutine, we do profiling of the usage of the reconfiguration switches in a way that we identify the ones which are the most needed. The inputs to this problem is the number of switch sets K, the total number of cells or modules M, and the set of solar irradiance Gn, comprising n different solar vectors. In step 1, we determine the atomic unit shape, series by parallel, S by P, where each atomic unit comprises M divided by the number of groups, K plus 1 modules. This which maximizes the flexibility. You could recall the combination with repetition, H. In step 2, we assume an atomic unit of S by 1 and reconfiguration switch between every one of them. In step 3, we apply the dynamic reconfiguration algorithm for every solar vector in solar irradiance Gn and record the number of usage of reconfiguration switches. In the final step, we identify the ones which step switches most often between series and parallel, and we select the K most ones, and then assume fixed series or parallel connection for the rest. We have run the experiments on MATLAB environment using function fmincon to numerically solve the open form PV equations for the whole array. We tested the algorithm for two spheres, two surfaces, a sphere with 60 PV cells and pyramid with 120 PV cells. One unrealistic assumption is that we assume constant temperature for all the PV cells and modules, but as our method is based on profiling, we could easily adapt the approach to consider temperature profiles. This slide shows an example of how the number of switches matter. If we use 59 switches, there's more flexibility such that we could increase the average power generation of 25 watts. If we use 9 switches, there's a dramatic drop in the number of switches, but the power generation is retained at 19 watts. Here, if you have the same number of switches, we show the impact of the location of the switches for this particular surface. If you look into the proposed method on the left side at the bottom figure, this one performs the baselines, which use uniform 3x2 atomic units and uniform 2x3 atomic units. And this outperforms the two scenarios by in terms of average power consumption by 8.6% and 31.3% respectively. So the locations of reconfiguration switches matter. This shows the results for 11 different solar irradiance vectors for the two scenarios each. And then for the pyramid surface and sphere surface, the proposed method outperforms all the baselines, which uses exactly the same number of switches. And lastly, I'd like to point out the trade-off between the number of reconfiguration switch sets and then the power generation. Our method retains a significant portion of power generation, 80%, with the reduced number of switches by placing them carefully in an array. Reduced wiring harness cost and then the costs are expected. I conclude the presentation by pointing out that this was the first work to cope with non-homogeneous operating conditions due to irregular surface using dynamic reconfiguration. And there are numerous expected applications as follows. Future works include joint optimization with the placement of PV cells and taking temperature variation into account. I think you're muted.
Yes, sorry, I was just trying to close Google Lens on. Any question from the audience? Very quick question also because we are close to the end of the session. Just a clarification, what do you mean at the end with the irregular surface? Because at the end, the pyramid and the sphere that you use are quite regular as surfaces.
Oh, I mean, like I mean that anything which is not flat is irregular.
Okay.
So regular, yeah. So it's something like conventionally, it hasn't been really considered. The electrical architecture for PV array on some sort of like curved surface and whatever, yeah.
Okay, and also I think that from the results, we assume that the pyramid surface is performing slightly better than the sphere one.
Oh, no. The purpose is not to compare different shapes of the surfaces. I mean, okay. The surfaces are inputs, and then the purpose of this paper is to find out the optimal like electrical circuit architecture for a given surface. Yeah.
Okay.
Yeah.
So thanks for the clarification.
Yeah.
Any other question from the audience? Okay, very good. Okay, I think that we are perfect in time. We are in time to close the session. Thank you everyone for attending this session, for attending these 4 nice papers. And also thanks for attending ICCD this year in this special condition. Thank you.
Thank you.
Thank you guys. And also obviously thank you to all the others.